So in the last class, we were looking at context-free grammars, and we also looked at a couple of examples. So this was the example of a grammar to generate strings with only matching parentheses. All right. And like I said, in a finite automaton, every state has a meaning. Even in a grammar, every variable has a meaning. So here the start variable, you can think of any, not only in this grammar, but any grammar, the start variable, you can think of the start variable as representing the final valid strings, because that's the idea, right? Only with the start variable, after you are done with the generation, you should land up in a string which is valid in that language, right? So the entire string is generated from one start variable. So you should think of the start variable as representing any valid string in the language. So in this language, the start variable represents a string with matching parentheses. So now, assuming you have a variable which represents a string with matching parentheses, now you should think, how do I generate larger strings, right? So like I said, there are two ways. If you have a string with matching parentheses, there are two ways of building larger strings out of it. One is you add another pair of parentheses around it to make it larger, or you concatenate another string of matching parentheses to this string to make it larger. Okay, so these are the two possibilities, and those two possibilities are captured in these two rules. S goes to ASB or SS or epsilon, that is to terminate the process, assuming A is the left bracket and B is the right bracket, right? So here we looked at few examples. So if this is the string that you want to generate, you should look at the nature of the string. Is it a string inside another, is it a string inside a pair of brackets, or one string concatenated with another? It is one string concatenated with another. So you should apply the rule S goes to SS, right? So each one of them is S. Now each of these is of the form ASB, because it is not like something inside something. It is just like a pair of brackets, right? And this is another example where you have a pair of brackets inside another pair of brackets. So this is like something inside something. So you can't use S goes to SS here. You have to use S goes to ASB, right? And then again, this S represents the inner pair of brackets. So this S should again go to ASB, and finally, this inner S will be replaced with epsilon. All right. So that's how you work out. So again, building finite automata, you need basically practice. There is no automatic way of building a finite automaton for a language. Similarly, writing grammars also comes with practice. There is no automatic algorithm to say, okay, if this is the language, this is how you will get the grammar for it. No, it's mostly practice. The best way, like I said, and I repeat every time, try to give meaning to each symbol. Try to give meaning to each state in a finite automaton. Similarly, try to give meaning to each variable in a grammar. Then it will be easier for you to build either a grammar or an automaton or whatever it is. Okay. Now let's look at one more example. So this is an example of a grammar that generates arithmetic expressions with only addition and multiplication. Okay. So there are three rules. Expression goes to expression plus term or term. Term goes to term into factor or factor. Factor goes to expression within brackets or some symbol A. So this A may be a number or whatever, some symbol. Okay. So now, what are the variables in this grammar? How many variables are there? Three variables, right? Expression, term, factor. Three variables. And what are the terminal symbols? Is A the only terminal? Are there no other terminals? There are other terminals also, right? Plus symbol, multiplication symbol, and that's it. Brackets also, left bracket, right bracket, they are also terminal symbols. They are not variables. They are some symbols. So any symbol which is not a variable is a terminal symbol. They are part of the string, right? In the final string that you're going to generate, those brackets will be there. So those are like symbols. Those are like individual letters. Okay. So you have five terminal symbols: A plus multiplication symbol, left bracket, right bracket. Okay. So given this grammar, we can generate these two sentences. I mean, we can generate more, two examples, two sentences as examples, and each of these sentences has a parse tree corresponding to it. Now, if you look at the first sentence, in that multiplication is given a higher precedence. Okay, whereas in the second sentence, these brackets, they are given a higher precedence. So in the first sentence, multiplication is performed first, whereas in the second sentence, the addition inside the brackets, that is performed first. So to make it easier for you, let me redraw them slightly differently so that you'll understand. So let me rewrite the grammar in slightly simple terms. So let's say expression goes to expression plus term, or term goes to term times factor or factor, and factor goes to expression within brackets or a terminal symbol. Okay, these are the rules. Now my sentence is a plus a into a. Now how do I build a parse tree for this? Okay, one way is you start with the start symbol, try to apply all different possible rules, and again try to apply all different possible rules and so on. Somewhere you will hit this sentence. That is one way. But that is like a brute force method, and it will become all the more difficult if you have LHS repeating in RHS, that too at the beginning of the RHS. Like for instance, if I take this rule, E goes to E plus T. So how should I write? Say E goes to E plus T. Now again, this E goes to E plus T. Now again, this E goes to E plus T, and so on. This will go on infinitely. There is no end to this, right? So I will never reach a sentence. So there is a way to solve this problem that we will look at it later. So this is top-down approach. You start with the start variable, try to apply all different possible rules, and somewhere you will hit the sentence. Okay. The other approach is bottom-up approach. You start with the sentence and try to work your way up to the start variable. All right. So if I start with the sentence, I can break it in two ways. Okay. I can say first focus on this addition and then the multiplication, or I can first focus on the multiplication and then the addition. Okay. So let me write both the possibilities. So in this case, I'll first focus on addition. In this case, I'll first focus on multiplication. Okay. So suppose if I first focus on addition, then I will try to match this portion of the string with some rule. So is there a rule which has plus symbol in its RHS? This rule, E plus T. Okay. But this is not E plus T. So first I need to reach E plus T from this stage. Okay. So the only rule where A is in RHS is F goes to A. Okay. So this A can be generated from F. Again, this A can be generated from F. Is there a rule like F plus F? No. All right. Now again, F comes from T. So this F can be generated from T. This F can be generated from T. Is there a rule like T plus T? No. But there is a rule like E plus T. So I can convert this. I can go back one step in this particular branch and make it E. Okay. So now, is there a rule like E plus T? Yes. So this rule has RHS E plus T, and this E plus T can be generated from E. So I can have another E that generates E plus T. All right. Fine. Now I have E. Is there a rule like E plus or E into something? No. Now, no matter how much you try, from this A you can get F, from this F you can get T. From this T you can either get E or you can stop at this T. Whatever you do, there is no E cross T, nor there is E cross E. None of those options are there. So you cannot proceed further. Right? So you cannot build a parse tree if you start like this. So if you try parsing the string in this direction, you cannot build a parse tree, right? So this branch does not go anywhere. So you try parsing the string in a different way. So try to focus on the multiplication first. Okay. So if I focus on the multiplication first, is there an expression with multiplication? Yes, t cross f. So for me to reach there, first I will generate this a from f and generate this a from f. Is there f cross f? No, but there is t cross f. So I will generate this f from t. Now there is t cross f. This t cross f can come from t. So I will add another t. This t can generate t cross f. Okay. Now is there an expression like something plus t? Yes, e plus t is there. Can I reach e from this a? Yes. So I'll get this a from f, I'll get this f from t, and I'll get this t from e. So now I got e plus t. This can come from another e. So e can generate e plus t. That's it. Now the entire string is covered. So this is the right parse tree. Okay. So basically, it is forcing you to generate the string only in one possible way. That is, you have to give precedence to multiplication. So why do I say this is giving precedence to multiplication? So let me just redraw it slightly differently. Same rules. I will just say, okay, e goes to e plus t. So e goes to e plus t. This e goes to t, this t goes to f, this f goes to a. So this e goes to t, this t goes to f, this f goes to a. Okay. Now this t goes to t cross f, t cross f. Now this t goes to f, f goes to a. So this t goes to f, f goes to a, this f goes to a. Okay, same tree. I just drew it slightly differently, nothing else. Okay. Now let's imagine I give values to them, like the expression 3 plus 4 into 5. So assume this a's value is 3, this is 4, this is 5. Now, how does the tree evaluate this expression? For me to get the value of this e, I should first know the value of this e and this t, right? Only then I can add them. But for me to get the value of this e, I should know the value of this t. For that, I should know the value of this f. Okay. So what happens? This value is percolated up the tree. So f becomes 3. Again, this is percolated up. T becomes 3. This is percolated up. This e also becomes 3. Okay. Now, for me to know the value of this t, first this t's value I should know, this f's value I should know, and then I can multiply and give that value to this t. Okay. How do I get the value of this t? Again, this value is percolated up. This f becomes 4. This is percolated up. This t becomes 4. Now this a's value is percolated up. This f becomes 5. Now this 4 is multiplied with 5, and that value is given to this t. Okay. Now I got the value of this e and this t. I can add them and I will get 23. Got it? Now, in this process, which operation needs to be performed first? Multiplication, right? For me to add these two, this value I should know. For me to know this value, this multiplication should be performed first. So the lower an operator in a tree, the higher its precedence, because here the values are being calculated bottom up. From the bottom, you are performing calculations and percolating those values up the tree. Okay, so the values can come bottom up. So whichever operation is at the lowest level, that operation will get the highest precedence. Okay, so this grammar forces us to give higher precedence to multiplication. In this case, you tried to give higher precedence to addition, but then it didn't work. You could not finish the parse tree. So that route of parsing will not work. You are forced to parse the tree only in this way. You are forced to parse the string only in this way. That is to give higher precedence to multiplication, which means you will have to perform multiplication first and only then addition. Okay. Now suppose I modify the grammar slightly. So the same grammar, let me take, I think I already have it copied. So let me paste it. No, I don't. So this same grammar I will take, and what I'll do, I will modify, I will swap addition and multiplication. So here I will say this is E cross T and this is T plus F. Now what will happen? Addition will get a higher precedence and multiplication will get a lower precedence. Okay. So now if I am given this string A plus A into A, now I can generate it in only one way. First, E should be replaced with E cross T, and then this E will be replaced with T. Sorry, not T. Yeah, this will be replaced with T. This T will be replaced with T plus F. Okay, and then this will be replaced with F. This will be replaced with A. This will be replaced with A. This will be replaced with F. This will be replaced with A. Now I got A plus A into A. Now you see plus has come at a lower level. So addition needs to be performed first and then multiplication. Now what values will you get? So assume this is 3, this is 4, this is 5. So here this will be 3, this will be 4, so this will be 7, and this will be 5, this will be 5, this will be 7. So 7 into 5, you will get 35. So you are getting a different value because you are performing addition first. So which operation to perform first does not depend on whether that operator comes first when you traverse from left to right. It depends on the kind of parse tree you get, and the parse tree depends on your grammar. Okay, so this hierarchy tells you which operation to perform first, and this is possible only with a data structure like tree. So this is an example of a very good use case of a data structure. Here tree data structure is actually solving your problem of specifying the hierarchy of operations to a machine. If you just give a linear data structure like array or linked list or whatever, that cannot capture this hierarchy. A tree can capture. So this is an example of a use case of a data structure. Got it? Okay. So depending on the grammar, the computer knows. Like I asked you earlier, how does the computer know which operation to perform first? How do you specify the hierarchy or the precedence of operations to a computer? One way is you just see, okay, you traverse the string from left to right, whichever operation you get first, perform it first. Sometimes you may get plus first, sometimes you may get multiplication first. So in one case you will do addition, in another case you will do multiplication. It should not work like that. Whatever is the order of the operations, you should always perform higher precedence operations first. So how do you specify that to a computer? This is how you specify. By giving a grammar and using this grammar by constructing a parse tree, and the parse tree will give you the hierarchy. Okay, so this is how actually parsing is done in a compiler. Parser is one portion. So whenever you give arithmetic operations in your program, it parses that and builds such a parse tree and then proceeds to the next stage. Okay. All right. So basically so from this, a high level understanding of this grammar is, you see, you can think of the term as a multiplication expression. Okay. So what we are doing is, first we are performing multiplication, we are getting a multiplication expression. Now this multiplication expression we are using inside an addition expression. Okay. So now it is forcing me to perform multiplication first and get a multiplication expression, and then use this multiplication expression inside an addition expression. Okay. But what if I want to perform addition first? Then what you can do, you can put that addition expression inside this bracket expression, so that bracket expression is given a higher precedence than even multiplication expression. And that is how it is usually in programming also, and even in normal mathematics also. Anything which is put inside brackets, that gets the highest precedence. Then other operations like multiplication, division, and then addition and subtraction. Okay. So first you get a bracket expression. It's not necessary that you get a bracket expression always. Here the bracket expression is given the highest precedence. this bracket expression you can use in a multiplication expression, and that multiplication expression you can use inside addition expression. Okay, it's not necessary that you should perform all the operations. You can stop in between. I can just stop with the bracket expression. I can just say put a inside brackets and say this is my expression. That is fine. Or you need not even always use brackets. You can just say a cross a. You can stop there. That is also fine. You need not always have addition. But if you are having addition, and then it will be part of this larger addition expression, but it will treat this as one unit. So you are putting this unit inside an addition expression. So which things you are clubbing, that is important. Okay, so I am clubbing the multiplication expression together as one unit, so that that unit is evaluated first before I proceed to the next expression. Okay, so that is the idea. So I am forcing it to do multiplication first. But if I change the grammar in this way, here I am first performing an addition operation to get an addition expression, and then I am using this addition expression inside a multiplication expression, that is this one. So here I am giving higher precedence to addition. Here I am treating addition as one unit and then using that unit inside another expression. Okay, so this is a high level view of the grammar. So this grammar is not arbitrary. Everything has a meaning here. E has a meaning, T has a meaning, F has a meaning. Okay, so in this grammar, F can refer to either a terminal, just one number or symbol or whatever it is, or it can refer to a bracketed expression. And here T can refer to either a factor, which means a bracketed expression, or a number, or it can refer to a multiplication expression. And this multiplication expression can be taken as it is, or this multiplication expression can be used inside an addition expression. So E will refer to either an addition expression or just a multiplication expression, or it can refer to just a bracket expression, or it can refer to a terminal. Okay, so this is a high level view of understanding this grammar. Okay, so each of these has a meaning. So that's what I'm trying to tell you. Each of these expression has a meaning, term has a meaning, factor has a meaning. These are the meanings. Okay, so if you understand those meanings, it will be easier for you to build the grammar or even understand a grammar. Okay, all right. Any doubts? Okay. And now if you notice this tree, so here this bracketed expression is evaluated first. You see, basically this bracketed expression is inside this tree where this thing is the root. You can think of it like this. So this term is generating this sentence. So first this needs to be evaluated for you to proceed to this, right? So this addition will be performed first, and then this value will be multiplied with this. Okay, so here multiplication will not be performed first, although multiplication has a higher precedence than addition. Why? Because you're having brackets in between. So brackets will have a higher precedence than multiplication. So the expression inside the brackets is evaluated first. Okay, so whatever is there inside a particular subtree, that will be performed first. In this case, this is inside this subtree. Okay, so this subtree needs to be evaluated first before you can proceed to this larger tree. That's the idea. Okay, fine. Now let's proceed further. So these are some tips while designing a CFG, how to build a grammar. Just some tips. Like I said, there is no automatic algorithm to build a CFG, but some tips like if you remember, if you want to build an automaton, or if you are given a problem with subproblems, you basically break it down into subproblems, then solve each subproblem and then combine the subproblems results to get the combined solution for the original problem. Something similar to that. There is no automatic way to construct a CFG for a specific context-free language, but some of the following methods will be helpful, either singly or in combination in constructing a CFG. So the first tip is, usually many context-free languages are the union of simpler context-free languages. So if they are a union of simpler context-free languages, what you do, you take these sub-context-free languages and solve or build a grammar for each of them, and then combine these grammars to get the combined grammar for the combined CFL. Okay, so one can merge different CFGs by adding a new rule like this. So suppose you have grammar 1, grammar 2, and so on. Now each of these grammars will have a start variable. You combine these grammars by just adding a new rule, a new start variable whose RHS is a combination of the old start variables. This is like union of multiple finite automata. You have many automata. You just add a new start state with epsilon transitions to the old start states, right? So suppose if I have say 2 grammars, like let's take the previous 2 examples, say matching brackets. What is the grammar? Like ASB or SS. So in this case S1, S1 or epsilon. Suppose my second grammar has some rules like maybe say AA or BB, and maybe A goes to, just for example sake, A goes to left bracket, B goes to right bracket. So now there are 2 grammars. How do I combine them? I add a new rule which says S goes to S1 or S2. So now, so basically, this is my grammar G1. This is my grammar G2. This entire thing will be my grammar G. So this G can generate all the sentences generated by this grammar as well as this grammar. This is like union of this language as well as this language. Okay, so that's how you combine grammars. Simple. Okay, so basically you start with this S. Using this S, you can generate all the sentences generated by S1, or you can generate all the sentences generated by S2. That's it. So this will generate the union of both the languages. Fine. So for example, suppose I have a CFL which is a combination of, or which is a union of 2 CFLs, 0 power n, 1 power n, union 1 power n, 0 power n. Now since this is a union, you break it into 2 languages. So the first CFL is 0 power n, 1 power n. The second CFL is 1 power n, 0 power n. Okay. Now for each of these CFLs, construct the CFGs. So for the first language, the CFG will look like S1 goes to 0 S1 1 or epsilon. For the second language, the CFG will look like S2 goes to 1 S2 0 or epsilon. All right. Now combine these 2 CFGs by adding a new rule, S goes to S1 or S2. That's it. This is the CFG, combined CFG for the combined language. That's all. Okay. Second tip, if you have a regular language, then constructing a CFG for it is much easier. You need not, so this can be in some sense automated, given that you first build a DFA for that. You know, some language is regular, suppose A star, B star. This is a regular language, right? You first build a DFA for that. And once you have the DFA, now you can directly convert that into a grammar automatically, mechanically. How? For each state, QI, you add a new variable called Ri. Now you add a rule, Ri goes to ARJ if QI goes to QJ on A. Okay, so suppose I have say 3 states, Q1, Q2 and Q3. Say Q1 goes to Q2 on A, Q2 goes to Q3 on B. So what I will do, this is my DFA. Not DFA, assume this DFA. I will have a rule, a variable in the grammar, okay, corresponding to each state. So R1, R2 and R3, and I will create rules. R1 goes to A, R2, because Q1 on A goes to Q2, and R2 goes to B, R3, because Q2 on B goes to Q3. Okay, now suppose Q3 is also an accept state. Then I will add another rule, R3 goes to epsilon. Okay, that's all. So given a DFA, you can mechanically convert it into a grammar. All right. So this is how you write regular grammars. Fine. Okay. And then the third tip, suppose if you have a language in which the portions are connected, for instance, in 0 power n, 1 power n, number of zeros are linked to number of ones. Okay. So if you have such strings, then you can construct a CFG by using a rule of the form R goes to URV. So here U and V are connected, which generates strings wherein the portion containing the U's corresponds to the portion containing the V's. So because we know number of zeros and number of ones are same, what are we doing? We are saying, say, R goes to 0, R, 1, or epsilon. So here, every time I get a 0, I am also getting a 1. So if I get 2 zeros, I'll get 2 ones. If I get 10 zeros, I'll get 10 ones. Okay. Suppose if I want to generate a language like 0 power n, 1 power 2n, then how should the rule look like? Right. So here the rule should look like R goes to 0, R, 1, 1. Okay. Now suppose n is greater than or equal to 0. What should be the terminating rule? Yeah. Epsilon, which means empty string is also accepted. Suppose n is greater than or equal to 1, then what should be the terminating condition? 0, 0, 1, 1. Because minimum 0, 1, 1 you should produce. You cannot produce an empty string. The smallest string that you can produce is 0, 1, 1. So you replace it with 0, 1, 1. Okay. So depending, again, this is important. You should check whether n is greater than or equal to 0 or whether n is greater than or equal to 1. Depending on that, your terminating condition will be decided. Okay. All right. Okay. Now leftmost and rightmost derivations. So before going through this slide, let me give you an example. So let's take the previous example. So let me take this. And let me consider the sentence, the same sentence, A plus A times A, and this is the parse tree. E goes to E plus T, and then this E goes to T, this T goes to F, this F goes to A. Okay. And this T goes to T cross F, this T goes to F, this F goes to A, this F goes to A. Okay, I got A plus A into A. Fine. Now this is the tree. Okay. Now I can also derive this sentence by applying rules one step at a time. Right. I told you there are set of rules, and then there is a sequence of applying these rules to get a particular sentence. There is a derivation of a particular sentence. All right. So there can be different sequences of derivations, like leftmost derivation, rightmost derivation, and neither leftmost nor rightmost. Okay. So let's say I start with E. The rules are clear. What rule I should apply at each step, that is clear. So E goes to E plus T. Okay. So this E goes to E plus T. Here also E will go to E plus T. Here also E will go to E plus T. Okay. Now I have a choice. Either I can first substitute this E or this T. Okay. If at every step I substitute the leftmost variable in that step, in all the steps in the derivation, then the derivation is said to be leftmost derivation. If at each step I choose to substitute the rightmost variable in all the steps, then that entire derivation is said to be rightmost derivation. If in some steps I replace the leftmost one, in some steps I replace the rightmost one, or I replace the middle one, whatever it is, then that is neither leftmost nor rightmost. Okay, so here I choose to replace this E. Here I will choose to replace this T. In this case, I have only either left or right, so I will say choose this one. Okay, so this E, what should I replace with? You can look at the tree. It will tell you what rule. This E is replaced with T, right? So this expression will become T plus T. Okay. Now I have to choose this leftmost variable because this is leftmost derivation. Okay. So let me finish this leftmost derivation first, then I'll move on to the other ones. So this T will be replaced with F. This becomes F plus T. Now again I have to replace this F. This F will be replaced with A. Now I am left with only one variable. I have to replace that. This T will be replaced with what is the rule here? This T is replaced with T cross F. Now this is the leftmost one. This T will be replaced with F. This F will be replaced with A. This F will be replaced with A. Okay, now let's do this. This T will be replaced with T cross F. This is the rule, right? This T is replaced with T cross F. So the rule will not change. Only the order of substitution is changing. You're not changing the rule. T is being replaced with T cross F only. T is not being replaced with F, or the first T is being replaced with T cross F only. The second T is being replaced with F only. Okay, so the rules are not changing. Only the order in which you are applying them is changing. Okay, so this T will be replaced with T cross F. Now what is the rightmost variable in this? F. So I have to replace this first. So I'll get E plus T cross A. Now what is the rightmost variable? T. What will I replace it with? F. This second T I am replacing with F. Okay. So E plus F cross A. Rightmost variable is F. What will I replace it with? A. Now only one variable is remaining, that is E. E will be replaced with T. T plus A cross A. T will be replaced with F. F plus A cross A. F will be replaced with A. A plus A cross A. You got the same string. Okay. The only difference between leftmost derivation and rightmost derivation is the order in which you are substituting the variables, not the rules which you are using. The rules are not changing. If the rules change, the sentence will change. But if the order changes, sentence need not change. Okay. Now let's consider this one. E will be replaced with T. This is the second E, right? This is the first E. This is the first E. This is the second E. Here, second E is being replaced with T. That's all. T plus T. Suppose now there is no specific order that I need to follow. Suppose I will choose to replace this one, not the leftmost one, but the rightmost one. What will this be replaced with? T cross F. T plus T cross F. Again, I can choose anything. I'll choose the middle one. Here I am free to choose any variable to replace. What is the middle one replaced with? F. Say now I'll choose the left one. This is replaced with F. Now I'll choose the rightmost one. This is replaced with A. Now I'll choose the leftmost one. This is replaced with A. Again, you are getting the same string. Okay. So for a given parse tree, for a given string in a grammar, you will there will be one parse tree. There can be more than one. I will cover that case later. Normally, if it is an unambiguous grammar, there will be only one parse tree. But there can be many derivations, more than one derivation. But leftmost derivation will only be one. Rightmost derivation will only be one. Other derivations can be many. Because you can sometimes choose the left one, sometimes middle one, sometimes right one, again left one, and anything. You can have umpteen number of combinations. But leftmost will always be one. Because in the left hand side there is only one variable. So if you are applying the same rule, there is only one leftmost derivation, right? Similarly, in rightmost there is only one rightmost derivation. So if there is one parse tree for the string, there is only one leftmost derivation, there is only one rightmost derivation. Other derivations can be many. Okay. So if for a grammar, if for every string there is only one parse tree, which in turn means there is only one leftmost derivation and one rightmost derivation, that grammar is said to be unambiguous. If for a grammar, for at least one string, if there is more than one parse tree, okay, it will automatically indicate there will be more than one leftmost derivation and more than one rightmost derivation. Any one of these can be your criteria. You need not look at all three criteria. Parse tree, leftmost derivation, rightmost derivation. You can take any one of them as your criteria. Suppose I take only parse tree as my criteria. If for a string, there is only one parse tree always. If for every string in the grammar, there is only one parse tree always, that grammar is said to be unambiguous. If for at least one string in the grammar, if there is more than one parse tree, that grammar is said to be ambiguous. We'll just look at an example in a minute. Now the same thing, you can replace parse tree by the leftmost derivation or rightmost derivation. That word parse tree replaces one of these two. They are unique. Parse tree is unique, which means leftmost derivation will be unique, rightmost derivation will be unique. If parse tree is not unique, then leftmost derivation will also not be unique, rightmost derivation will also not be unique. Okay, so let me cover those first. So first of all, leftmost and rightmost derivations. Every string of symbols in a derivation is called a sentential form. Okay, let me mention that also. So basically, if I consider this last one, actually, this last one is called a sentence. Okay, whatever final string you are getting with only terminal symbols, that is called a sentence. So the leaves of the tree, the leaves of the parse tree, when you connect them, whatever you get, that is a sentence. Okay, but to reach this sentence, you are going through many intermediate sentences. They are not really sentences, those are called sentential forms. All right, so all these including the last one, they are called sentential forms. Okay, so sentence is a special sentential form that has only terminal symbols. If you have at least one non-terminal symbol, that is not a sentence. That is just a sentential form. But if you have only terminal symbols, that sentential form is said to be a sentence. Okay. Every string of symbols in a derivation is called a sentential form. A sentence is a form that has only terminal symbols. A leftmost derivation is one in which the leftmost non-terminal in each sentential form is the one that is expanded. right? In leftmost derivation, you replace the leftmost variable. A rightmost derivation is one in which the rightmost non-terminal in each sentential form is the one that is expanded. Okay? Leftmost and rightmost derivations, we're continuing that. A derivation may be neither leftmost nor rightmost, like we saw the third case. Change in derivation order does not change the language generated. That's what we saw. When you are shifting from leftmost to rightmost, only the order is changing. The rules which you are applying did not change. It is the same parse tree, same rules from the parse tree you have taken, and you are applying the same rules. Only the order in which you are applying these rules has changed. Nothing else changed. So change in order does not change the sentence, does not change the parse tree. Only if you change one of the rules, only then the sentence will change. All right. So if I take this parse tree is giving me only the rules that I am applying at each stage, right? This E will be replaced by E plus T. This T will be replaced by T cross F. These rules only parse tree is telling me. Parse tree is not telling me, suppose if I have 3 children, it is not telling me which child I am replacing first. It is not telling me the order. It is only telling me the rules. But a derivation is telling me both the rules and also the order in which I am applying those rules. Okay? By choosing alternative RHSs of rules with which to replace non-terminals in the derivation, different sentences in the language can be generated. So if I have to generate a different sentence, it's not sufficient for me to change the order. I have to change the rule. Then the parse tree will be different, and hence the sentence will be different. Okay? Relation between parse tree and derivations. A parse tree is order agnostic. Like I said, parse tree only tells me the rules. It does not tell me which child I am replacing first. Okay? It captures the rules applied, but not their order. A derivation captures both the rules applied as well as their order. Hence, multiple derivations can map to the same parse tree, but multiple parse trees cannot map to the same derivation. Because multiple derivations can have the same rules applied in different order. So they can map to the same parse tree. But multiple parse trees means you have changed the rules. You cannot apply it to the same derivation. Okay? For every leftmost derivation of a string W, there exists an equivalent rightmost derivation of W generating the same parse tree. Hence, these orders are equivalent with each other and also the corresponding parse tree. Okay? So, given a parse tree, there will be an equivalent leftmost derivation and an equivalent rightmost derivation. So, if you have 2 parse trees, you will have 2 leftmost derivations, 2 rightmost derivations. If you have 10 parse trees, you will have 10 leftmost and 10 rightmost derivations. Okay? So, this is the equivalence. A grammar is ambiguous if and only if it generates a sentential form that has 2 or more distinct parse trees, or 2 or more leftmost derivations, or 2 or more rightmost derivations. Any one you can take as the parameter. So this is an example of an ambiguous grammar. So the same grammar which we saw earlier, rather than having 3 different terms, expression, term, and factor, we are having expression for everything. So expression can be of the form expression times expression, or expression plus expression, or expression in brackets, or terminal symbol. Now using this, you can get 2 parse trees for the same sentence. These are 2 different parse trees. So in that parse tree, which operation is given higher precedence? Addition. Plus is given a higher precedence. You see, what is the subtree? That expression subtree is 1 unit. So addition is performed first, and then multiplication is performed there. In this tree, which is given higher precedence, multiplication. So now, if you write this grammar, if you build a compiler with this grammar, when you give a plus a into a as an input to your compiler, the compiler gets confused which parse tree to use. There are 2 parse trees. One parse tree is telling me perform addition first. Another parse tree is telling me perform multiplication first. What should I perform? So it is confused. Okay. So to avoid that confusion, we should convert this ambiguous grammar to unambiguous grammar. That is the previous version we saw. Mostly ambiguous grammars can be converted to unambiguous grammars. So that for every sentence, there is only one parse tree, there is only one meaning. Okay. So let's stop here. And